So my name is Russell O'Connor. I'm work in the Blockstream research. I'm here to talk a little bit about my formal verification work for libsecp256k1. Subtitled, "That Time I Almost Found a Bug in the Modular Inverse Code of libsecp, but in the end it turned out to be fine." So we're going to go over how we reason about C code formally using formal proof assistant. Let's get started. So part of my time is spent using formal methods to verify the correctness of libsecp. We're using the verified software tool chain, which was developed in Princeton. It is I guess a framework for the Rocq proof assistant. Now, the Rocq proof assistant was renamed the Rocq proof assistant earlier this year, but all my slides and stuff use the old name. And so for this presentation, I'll use the old name just to be consistent with everything, but be aware that the project is now called Rocq, R-O-C-Q, if you need to look that up. Now, the basic way it works is that you write formal specifications of all the routines that you're going to verify, and then you reason about the C code itself to prove that the C code meets those formal specifications that you've written. Some of you are probably familiar with libsecp256k1. This is an optimized cryptographic library that Bitcoin uses for digital signatures. It replaced OpenSSL, which was in the original Bitcoin code. And we'll be focusing on the modular inverse function, which is to compute the inverse modulo some specific prime number P. There are two prime numbers that are used in libsecp. The field modulus for the elliptic curve, and then the group order of the elliptic curve itself are both large 256-bit prime numbers. And somewhat recently, I mean, it's a little like 5 or more years old now, right? But there was a new SafeGCD algorithm designed for doing fast constant time modular inverse, and libsecp now uses that SafeGCD algorithm to do the modular inverse. So it was a bit of a new code, and it was a nice target for verification efforts for trying it out, because it is non-trivial, right? So if we can reason about the modular inverse, there's really nothing stopping us about reasoning about the entire library, for instance. So it was there are a couple other things we could have verified, and we certainly verified along the way, but we want to practice something a little bit meatier rather than just a toy problem, which is a little bit easier to do. But we're going to start easy, right? I just want to give you a flavor for how the formalization works. So the first thing we're going to look at is this umold128 function, which takes two inputs A and B and multiplies them, 264-bit inputs, and multiplies them together, and returns the low 64-bit of their product, and then also returns the high 64-bit of their product. And here we're just looking at a bit of actual C code that implements this without using hardware intrinsics, just by making use of 32-bit multiplication. And the first thing we need to do is write a specification, right? And so we have a function signature. Oh, sorry, yeah. Before I go on to that, so in order to reason about C code, we have to take this text and get it into the Rocq proof assistant. And there's a program called Clightgen, which takes the program and then turns it into, it parses it and produces the abstract syntax tree, and then creates some Rocq code for the abstract syntax tree of all the functions we care about. And this is a function that we were just looking at. And if you look at it as an abstract syntax tree and put it into the Rocq proof assistant, it ends up looking a bit like this. So it's just the syntax tree version of that same code. And in order to reason about this code over here, the first thing we're going to do is give it a specification. And you can think of a specification as sort of like a formal extended version of a function signature. And that's going to be in this little block I've highlighted over here. So I think the most important part of the talk is like, if not learning to like read these formal specifications, you know, understanding what goes into a formal specification of a function. And so let's look at this function over here, right? So we have this declaration, we have the name of the identifier over here, right? And then we have these parameters, which are a:z, b:z, high val, and sh:_share, right? So these are parameters of the specification, which are not quite the same as the parameters of the function itself. In particular, these are, this is sort of a mathematical universe of objects, right? So this z over here is like the full natural, full set of integers from mathematics, from -infinity, +infinity. And so we're saying a is some mathematical integer and b is some mathematical integer. And then high, this :val, these are the type of c values that I could be going, that are, it's just the type of the mathematical type of c value. So high is some sort of c value, and sh is a share, which I'll talk about in a moment. All right, so we're going to say basically for all a, b, high, and sh, the following goals, right? The next line over here is just a restatement of the types of the arguments that we saw from the original type signature over here. So we have a ulong, and a pointer to ulong. That's just a restatement of the actual parameters of the function, which are distinct from these mathematical parameters of the specification. And then we have some preconditions on our function. And the main ones are that our integer a is actually between 0 and the maximum value of a 64 unsigned 64-bit integer, so 2 to the 64. And b is actually going to be constrained to be have a precondition that it's between 0 and 2 to the 64. So for any a and b such that a is 64-bit and b is 64-bit, I'll come back to the share thing in a moment. We're going to have that the first argument is the C integer 64-bit representation of A, and the second argument is the 64-bit integer representation of the mathematical integer B, and the third value is this HI value, which is some sort of C value being passed in. And the thing, so if you went to the university like I did, we sort of covered preconditions and postconditions for reasoning about procedural code. But after my undergraduate, I graduated in 2000. The state of the art for formal reasoning about procedural code improved dramatically with the creation of separation logic. And the problem with reasoning about procedural code in the past is dealing with pointers, and in particular, the problem of aliasing, right? So you could say this pointer points to some value, and some other pointer points to some other value, and then you would have to have like a bunch of side conditions about those pointers aliasing or not aliasing, and it was just completely infeasible to reason about. Here we only have one pointer, so we don't really have an aliasing problem, but we'll sort of see that a little bit later. But the key thing of separation logic is this separating conjunction that they invented for reasoning about it. So this thing here says that the value of HI, which we said was some sort of C value, is a pointer and it's pointing to some block of memory that it's capable of holding unsigned long value. And this underscore over here says we don't really care what value it's pointing it to. It could be even uninitialized memory. So that HI input pointer is just pointing to, that's a precondition of the block of memory. And if we had other pointers, we could add more clauses to this separating conjunction statement. And it would say that not only do these pointers point to these various blocks of memory, but all these blocks of memories are disjoint. And that sort of like by default means that all the pointers are not, I mean, it's a little bit stronger than the pointers not aliasing. It's just that all the blocks of memory are disjoint from each other. And so they were able to turn that into a logic that we can use to reason about code, which is and then it turns into a practical system where we can actually reason about the code. We'll get into reasoning about it later. So that covers sort of the preconditions of our formal specification, and then we get on to the postcondition where we have a statement of the return type. It's just a restatement of the function signature that we saw over here. It returns an unsigned 64-bit, which is a long. We have no propositional conditions in our case for the postcondition, just that we have a specification of the return value, which is that it returns the product of A and B converted to a 64-bit integer, right? And so remember that A and B are mathematical integers, and the product is potentially 128 bits in size. And so this int64 repr function, which converts mathematical integers into C long types, does that conversion just by taking it modulo 2 to the 64. So this int64 repr is actually taking the low 64 bits of the product, of the mathematical product of the integers A and B. And then for the postcondition about the heaps is that this high pointer is still pointing to a long piece of memory, and now that memory as a postcondition holds a particular value, which is the integer product of A times B shifted by 64 bits to the right. So this gives us our high 64 bits of that product, and then that's converted to a C integer 64 and put it into a long value over here. Now I'll just go briefly mention this share stuff parameter. We have this notion of shares. This is really only relevant for multi-threaded code, and so we won't really talk about it too much over here, but this basically says that this share embodies the write permission. It's similar to, you could sort of think of it as that we have the capabilities of writing to the share, or the share holds the writing capabilities. And then here we've said that the pointer HI has this sh share, which includes the writable share. So we have the capabilities of writing to this bit of memory over here. And when we return, we still have the same capabilities that we started with. So that's the formal specification of this multiplication function. Maybe I'll pause for a moment to see if there are any questions. Okay, and so we want to actually reason about that code. So we have the formal syntax tree embedded into it. So I guess I should mention that, yeah, let's go down to the proof over here. Now, this is the Rocq proof over here on the left-hand pane of the screen over here, and it's basically completely inscrutable to being read, right? So this is the actual source code, if you are, and it's inscrutable because it's really just a transcript of your interaction with the proof assistant, right? And so in order to like understand what's going on, I've used this tool that takes the Rocq proof assistant, runs all the commands, and keeps a transcript of that interaction. So we can browse the proof as if we were running the Rocq proof assistant. We can't, of course, do any editing or changing, but it'll show the internal state on the right-hand pane that we go through when reasoning about C code. So we'll just quickly go through this proof. And so when you're using the interactive theorem prover, you sort of like step through these commands. Like here we do the start function, which sort of prepares our proof as part of the verify software toolchain thing. And it just like, we have this formal specification here that we've defined and attached it to the formal C code, which is this F underscore thing. And when we start the function, what it does is it prepares everything. It loads up all the preconditions into our context over here. And we have a goal, which is to prove that the program, starting from its preconditions, meets its post condition, which is sort of elided over here. And rather than writing out the entire contents of the body of the function, it just writes out the first line, or the next line to be proved, which in this case is the first line of the code. And then the rest of the code is like elided in this little macro over here. So the first line of the code is to set the variable LL to the product of A and B. In the underscore A and underscore B are the representations of the C variables A and B, which are distinct from the mathematical variables A and B, which are like mathematical integers. And we can see here we have in our context that the C variable A currently holds the value of the 64-bit representation of the integer A that was part of our preconditions, and similarly for B and so forth. If we look at the program over here, it's basically a straight line program without any branches or loops or anything like that. So it's actually pretty easy to reason about. We can just like run through the entire program with this repeat progress C and get right to the end of the program, where we end up with a goal of, we actually end up with two goals. One is to show that the output type, which we said was supposed to be the low 64 bits of A times B. After running the program, the return value seems to be like this complicated expression. And then we have to show that this complicated expression is in fact equal to our post condition value that we want. And similarly for the heap condition is that we said that we want the heap post condition to be the high 64 bits of the product of A and B. And if you just run the code through the straight line evaluator, we know that the code is pointing to this crazy value over here. And again, we have to reason about the code to prove that this crazy value is in fact equal to the high 64 bits of that. And that's what the rest of the proof does. It's basically doing mathematical reasoning about these values. And we just like, this is sort of standard proof assistant stuff where we, go through our goal over here and keep on like manipulating it mathematically again and again and again. And eventually with enough mathematical manipulation, we see that in fact that value was equal to our goal value, and we can solve it. And then we can move on to our second goal over here about the heap. And we run sort of the same process as we did before of mathematically reasoning about these values over here using standard commands from the proof assistant. And eventually we reduce it to the same value as we were trying to show, and we solve it there. And that finishes the proof of correctness of that bit of code, right? So hopefully that gives you sort of at least an inkling of how it is that we can even reason about C code formally at all. Any questions? Go ahead.
Yeah, just to clarify, the first step was taking the actual C code and then giving it, I forgot what the name was, to some program that produces the like formal something, the verifiable C.
Yeah, so the first step over here, I think you're talking about this thing over here.
Yes.
Is that we took the C code, ran it through this program called Clightgen to take the C code, and because we have to reason about it, we have to get the C code into Rocq, right? So what it does is it basically got a parser for C code. It creates an abstract syntax tree and then converts that abstract syntax tree into a bit of a data type with inside the Rocq proof assistant. And the value of our function with that Rocq data type representing the syntax of the C code is this.
Okay, so none of the proving ever operates on a binary or any like actual compiled code.
No. So the verified software tool chain is built on top of the it's built on top of COPCert, which is a European project for building a verified C compiler. So COPCert has a set of formal C semantics for its compiler, and it proves that the assembly code generated by its compiler matches the semantics of the C language that it defines for its compiler. The verified software tool chain builds on top of those semantics. So when I prove something is correct in the verifiable software tool chain, it means it meets the semantics of COPCert, which means that if you were to compile the C code with COPCert, it would produce assembly that matches that that code, that proof. Yeah.
Okay, thanks. And one more question: like, what do the error messages look like if, for example, in the spec you change the multiplication to a division? Like, how useful is the error you get from from Rocq?
Like, it's probably the case that it is very sensitive to changes. Like, even making a tiny change that would like not even change the output of the function, right? Let alone making it wrong. In this case, you would be able to get all the way to the end of the function if you made just a small change to the specification, right? Let's say you change it to a division instead of a multiplication, like you said. Then, oops. Then over here in your C specification, you would have a division sign instead of a product over here, and you would be able to make it as far as this statement here. Except instead of here, we've proven that A times we were sort of reduced the right-hand side to A times B, but if your specification still had division over here, this would be a division sign over here, and then the reflexivity command would fail at that point in time.
Okay, so would you say, like, from your experience, that that output would be quite helpful in tracking down what's actually wrong? Would you say in your experience that's usually the case, or?
I mean, what happens is that you're working with interactive proof assistant. Like, you can see the completed code here, but when you're developing this proof, there's a sort of a little bit of backtracking, going back and forth to try to generate this this proof, and what happens is that you are just like unable to figure out how to generate the proof to begin with. So it's not like you get an error message, like, it's just that, like, well, I mean, if we had sort of that error in the specification, I would get to this point and I'd be like, oh, I can't do reflexivity like I expect, or something like that. But it can be a little bit more vague than that. Like, it's just like, how do I get from our hypothesis to our conclusion? And you end up lost, and then you need to like figure out what's wrong. It's sort of like it's very similar to reasoning about mathematics, like presented with a homework assignment, and you have to prove it correct or prove some theorem, and you're like, how do I do that? You don't really get error messages. You just fail to prove things.
Right. Okay. Thanks.
And we'll get a little bit of a hint of that later in the presentation. Let's talk about the modular inverse function in libsecp. So we'll get into the details of the algorithm at first, but let's talk about the signature and then the specification at first. So this is the the modular inverse function for up to 256-bit numbers. It has 64 here because it's for 64-bit machines. And the bar means we're looking at the variable time implementation of the algorithm. And it has two parameters. It has this x, which is a pointer to this secp mod 64 signed. This is basically a structure that holds an array of up to 5 elements, 5 64-bit integers. And then the mod info holds data about the modulus. And I won't go into too much detail about what this structure is. So it has these two arguments, and then the post condition is roughly that the value that x is pointing to is replaced with its modular in its inverse modulo, this value over here. And if the input is 0, then the output is also has to be 0. So let's look at the specification. Right. So now we have like a whole bunch more parameters. We have x again, which is a mathematical integer, m, which is going to be the modulus of mathematical integer, some value pointer x, some value mod inverse, a bunch of shares like we had before, and a set of global variables. All right, so here again we have a restatement of those two parameter types, and here's our sort of the meat of the precondition. We require that m is odd. We require that x is between 0 and m. We require that m is less than 2 to the 256. So remember, m is a mathematical integer, so it can be as big as you want it to be, right? So we've exceeded the 64-bit values that we had for parameters before. M can be as large as 2 to the 256. Require that m is a prime number, and then we have like the shares of various permissions for, so the share that we'll use for the pointer to x, we need to be able to write to it, so we have to have the write capabilities. And the other ones we just are going to be read only, and so we only require that they have read capabilities. So the parameters of the functions are initialized with this pointer x value and this mod info value, and the global variables are the global variables that are part of the declaration. And then again, we have this separating conjunction, right? So x is pointing to an array that represents the value x. This is something that we sort of had to define ourselves, right? But we defined our own signed 62 representation. So the array of up to 5 elements is sort of you can put them as 5 digits in base 2 to the 62. So a value is like the first element of the array plus the second element of the array times 2 to the 62 plus the third element of the array times 2 to the 124 and so forth. So that's sort of your base 2 to the 64 representation. The mod info points to the suitable modular information about m, which I don't want to go into right now. We have the Brown value from our global variables that we'll need. I won't go into too much detail. And we have this global variable which contains the signed 62 representation of the value 1 over here, right? So if you look at the code, we have this global variable which is read-only, which contains the value 1, and we'll need to, the code requires that exist. There's no return value in this case. The type is void. And so the only interesting stuff about the post condition is in the separation conjunction. All right. So of course, like I said before, the separating conjunction says that not only does the pointer point to these values, but all these blocks of memory are disjoint from each other. So right, this solves our aliasing problem. And our post condition is basically exactly the same because we only have read permission to these ladder pointers, right? So the only difference between the preconditions and the post conditions is that this pointer x, instead of pointing to its old value of x, is now pointing to the modular inverse of x mod m. So that's the formal specification for the modular inverse function. This is actually a specialized version of the actual specification. We actually give a more general specification that only requires that x and m be relatively prime rather than m being prime. And so what we actually do is we prove that the function meets this more general specification, and then we have a small theorem that says that any function that meets this more general specification also meets this more specific specification. And that allows you to, like in the very common case where m is prime, you don't have to worry about this x or equal to 0 conjunction. You can just use the more specialized specification instead of the general one. But just in case we ever need to use it in more generality, we prove the more general version of the specification. Let's just do a glance at the proof of the correctness of that function. So again, after start function, we have like our context with all of our preconditions up here, and then we have to prove this goal that we execute the entire program. We're going to meet the post condition in the end, and then we have all this. This is the sort of the local state about the local C variables, that the local variable T is pointing to this value here, and G and F and D. We didn't look at the code too carefully, but let's just glance back at it briefly. The first thing you do in the code is that we set the values for the array of D and E to basically be 0 and 1. And if we fast forward through the first 5 instructions, we see that indeed that we filled this array of D with a whole bunch of zeros in the array, and then we have to do manipulations to like say that when you have all zeros, that in fact is the signed 64 representation of the value 0, and similarly we fill in the values of E with a bunch of zeros and a 1 over here, and then we note that that particular array is actually the signed 62 representation of the value 1, and the value 1 over here. And so we just pulled that up over here. And then, we just keep on like working our way through it. We do some subroutine calls. We go through a bunch of functions, and it goes on and on and on and on and on and on and on. And after a whole bunch of work, we will eventually get to the end and get to the correctness of it. So that sort of gives you an idea of the scope of what we're dealing with. And of course, before we can prove the correctness of this function, we have to give specifications and prove the correctness of those for all the subroutines that are defined in the code. So that's all this stuff up over here. And yeah, it's quite a bit of work to do it. It's certainly not easy. But let's talk about the SafeGCD algorithm itself a little bit. I'll go back to my slide. So it's a very high-level overview. The way that the SafeGCD algorithm works is you initialize these two values, f and g, with the prime number p that you're taking at modulo and your input x, and you compute these sort of transformation matrices to sort of this iterative algorithm to update the values of f and g to be generally smaller, certainly not larger than before, and still maintain the same GCD value that they had before. So this is sort of this is how the GCD algorithms sort of work. And the key thing that makes it sort of fast is that that we sort of group, we sort of batch together a bunch of steps at once. So in our 64-bit implementation, we sort of batch n steps together, where n is 62. It matches our 62 representation, 2 to the 62 representation of integers. Right. So as we iterate this procedure, f and g get smaller and smaller and smaller, but until one of them becomes 0, which in particular will be g, because for reasons f is always odd. And because we preserved we set up our transformation matrices to preserve the GCD of f and g through these steps. When g gets down to 0, that means the value of f has to be the GCD of f and g. And of course, in our case, since f started off as prime and x was smaller than p, they have to be co-prime, and so the GCD is going to be either 1 or -1. So to compute the modular inverse, you take the basic GCD algorithm and you produce an extended version of it called the extended GCD algorithm, which sort of augments this stuff with 2 extra variables, d and e, which start off as 0 and 1. And then as you transform f and g, you're transforming d and e in a complementary way. And then when you get to the end, one of these values ends up being the modular inverse stuff. I don't really want to dive too much into exactly how the extended GCD algorithm works. But I do want to talk about f and g getting smaller and smaller. So if you go through sort of the explanation guide of the implementation, they have a bunch of Python Python reference implementation of it, including a bunch of optimizations talking about the batching and so forth. So if you really want to know how the SafeGCD algorithm works, this documentation is a great thing to read. And it will talk about many of the optimizations that appear in the C code in order to make this really fast. But if you go through the documentation, it'll mention that f and g get smaller and smaller. So the absolute value of these 2 entries in the matrix sum to less than 2 to the n, and the absolute value of these 2 entries in the matrix also sum to less than 2 to the n. And because we're dividing 1 by 2 to the n, it must be the case that the next iteration, the absolute value of f is less than the maximum value of the absolute values of f and g. And similarly, for the next value of g, it has to be bounded by the absolute values of f and g. Yeah, so this is just saying that you can see a description of the algorithm over there. Now there's this, I said that f and g are represented in the signed64 array of signed62 array of 64-bit values that have length up to 5. But as an optimization, as f and g gets smaller in the C code, the length value shrinks, right? So once they can fit into small enough to fit into 4 elements of the array, we can decrease from the length from 5 to 4. And then when we're looping over the numbers in sort of the subroutines, we only have to go up to 4. And then as f and g get smaller and smaller, this length will decrease to 3, 2, 1, and eventually g will become 0, and the algorithm terminates. But in particular, this length of the array, of the signed62 array, is just not mentioned in the Python code because the Python code works with arbitrarily large Python integers. So what happened is that when reasoning about this C code, I get to this line over here, which requires me to show that the highest lim of f and g fit in this signed 64-bit value. And I got stuck because I couldn't prove the precondition required to call this function over here. And I spent a lot of time trying to figure out why I couldn't meet the precondition for this subroutine. And here's the issue I run into, which is that we said that the absolute value of f and g is the maximum, bounded by the maximum values of the f and g from the previous iteration, right? And f and g in the signed 62 format are basically the same as two complement integers. And if you recall your computer science, right, when you have two complement integers, signed integers, right, you have this sort of half-opened range where the most negative value that is acceptable, which is going to be minus 2 to the 62 times length plus 1, there's this negative value, but the positive value is excluded from the range, right? There's no corresponding positive value in the same magnitude as this negative value over here, right? So the issue was, in some extraordinarily unlikely case, if the sum of Vn plus Un is negative 2 to the n, or if Qn plus Rn is negative 2 to the n, then the next iteration for f and g, because we're dividing by 1 over 2 to the n, it could be the negation of the original values of f and g. And if the value of g, for instance, were negative 2 to the 62, exactly negative 2 to the 62 times length plus 1, right? This next iteration would negate that value, leading to the positive value of 2 to the 62 times length plus 1, which is actually out of bounds. And so this is sort of exactly the nightmare scenario that we worry about. We have some sort of corner case over here, which is like basically impossible to hit by randomized testing, that if some attacker exploited could find some input that would tickle that, incredibly unlikely case where this matrix has values that sum up to exactly 2 to the minus 2 to the n. And then we would get an out of bounds value, which would lead to sort of like unpredictable or undefined or whatever behavior, which is then exploited by the attacker to do who knows what, because we haven't really thought through this program, right? So that was quite worrying. So I spent some time trying to find some matrices where some conditions in which the matrix would end up with u plus v equal to the minus 2 to the n, or q plus r equal to minus 2 to the n. But as it turns out, it's actually impossible. So if you do a more careful analysis of these matrices, it turns out that u to the n plus v to the n is always strictly greater than minus 2 to the n, and q plus r is always strictly greater to minus 2 to the n. And so it turns out that the f and g values can't go out of bounds at all. So what I had to do, I had to go back to my previous code that reasoned about the generation of these matrices and prove that it has this additional invariant that they're all strictly greater than minus 2 to the, these sums are always strictly greater than minus 2 to the n, and carry that invariant forward, and then I could finally meet my precondition that I was trying to prove in order to finish the correctness of that program. So this fact that the absolute values are less than, sum up to less than 2 to the n is mentioned in the Python guide, but this extra condition is not mentioned in the documentation anywhere. It is my belief that the authors of libsecp did not actually realize why their code is correct. I did talk to the authors afterwards, and they did tell me that they had done some previous ad hoc testing where the lim size, instead of being 2 to the 62, were actually very small. So it's possible that that testing would have picked up on this problem if the problem were actually a real problem, which it turns out is actually not actually a real problem. And yeah, so that concludes my presentation about that time. I almost found a bug in the modular inverse code of libsecp256k1, but in the end, it turned out to be fine.
Thanks, Russell. I saw Habasto had a question in the chat asking if such issues could be caught by fuzzing.
Well, again, right, it sort of depends on how smart this fuzzer is, right? And my understanding is that they are pretty smart. So it's maybe not impossible for it to be caught. But I don't know, you have to like, n is you have to get these matrices that sum up to, you know, the most negative value possible when, you know, minus 2 to the 62. And there's only like, if you just did randomized testing, that certainly wouldn't work, because it'd be a 1 in 62 chance at most, you know, sort of to encounter that. And whether the smarter fuzzer is smart enough to like reach those most extreme values, like, I don't know. I'm somewhat skeptical that it would have been able to find it. Of course, it's actually impossible, right? Because it turns out that it can't be reached, right? But if it were possible, I don't know. I don't know if fuzzers are actually smart enough to reach it. I would be greatly concerned.
Larry also had a question from earlier. I'm not sure which of the outputs he was talking about, but he was questioning the specification. It's hand generated, like what we want the function to do. Maybe just clarification on which pieces a human is doing.
Yeah, so there is a sort of a question of, you know, is this specification even what we want to specify, right? And well, first of all, like this specification, as bulky as the specification is, it is in fact quite a bit simpler than the C code itself by a significant amount. So it's more amenable to review. But I think in some ways, the more important answer is that as you, like, we have to do the same specification for like all the various subroutines we have up over here, right? But what's interesting is that those specifications sort of have to click with each other when you like reasoning about other functions that call those subroutines, right? So if those specifications are off or wrong or something like that, they tend to get sort of shaken out because you can't prove the correctness of the functions that call those functions if the specifications are wrong. And like, even if like these specifications are wrong in some sort of moral sense, by the time we get to this point over here, those specifications are sort of out. Let me illustrate that by a different story. The CompCert people used to have an error in their specification of C. And the error involved like the scoping of variables that are declared in like loops, like a for loop, right? So you can have declare a variable in a for loop, and the for loops variable is supposed to be scoped until the end of the for loop, right? But they had sort of some bug in their C specification that the scoping extended beyond the end of the loop, right? So so it would shadow other variables if you tried to use them, and it would just behave incorrectly according to the actual C specification, right? So it's wrong in that sense, right? And they did eventually fix it, right? But if we had like used that wrong specification of C to reason about this code over here, right? And we were to compile that with compcert, right? Because compcert is using, it's proven correct with respect to its formal semantics of C, which were incorrect at the time, right? The point is that we would prove the code correct, and if it's compiled with compcert, right, that C specification gets sort of cut away, right? So that even though the C specification is wrong, right, we still have that the assembly code meets the formal specification we wrote and does the correct thing, right? Because we were just working in an incorrect definition of C, right? But we proved end to end that the values of the assembly code are correct, right? So even if you have sort of intermediate things that are wrong, they sort of get cut away by this process, and you end up with the specification just your top level specification ends up being what matters. So that's a little bit of a fun story about how you can even be wrong in the middle of your specifications, and it doesn't matter. But usually what happens is that, in fact, and presumably what happened with the compcert people is that eventually someone was trying to prove something about a C code, and they're like, this doesn't make any sense, and they found the bug in the C specification, and they had to fix up their compiler. Michael has a question.
Yeah, I guess probably a lot higher level than sort of what you covered here. But recently there's sort of been a lot of, and I think this is one of the reasons we wanted to get you in to present, is just like seeing a lot of discourse around like formally verified like Bitcoin or a formally verified client or something. And looking at this, it seems like that is like an awfully big task and probably a long way away. I'm wondering, is that also your opinion, or like how far-fetched are these claims of like, yeah, we'll just end up with a formally verified Bitcoin D at some point?
Yeah, so my rough thinking is, not based on too much, is that it's about 10 times as much effort to prove programs correct than to like just write the programs itself. 10 is a bit of a random number, and it was probably a little bit more than 10 for verifying C code, but this is the first time I've actually reasoned about C code, and there's like a lot of things I've learned by the process, and I feel like if I were to do this a second time around, there are many things that I could do a lot better, and it might be closer to that 10x factor that I feel like is the right number. There's also a bit of a problem, is that I'm not a big imperative language correctness person, right? This is my first sort of foray into that. But I'm not aware of like a practical system for reasoning about object-oriented programs, right? This verifiable software tool chain is very specific to C, which is a procedural language, and extending that to an object-oriented language, like I'm not aware of any practical way of doing that today. And right, so like 10 times more expensive, right? Is it unreasonable? Like people are putting like millions or billions of dollars into like sketchy crypto wallets that end up getting deleted off their chain and stuff like that, right? So I always thought that like serious people should be, if you're gonna like put billions of dollars into some sort of smart contract or some sort of crypto system, like, why not spend millions of dollars to verify the correctness? I don't know. You can see that, even in Bitcoin, which has like trillions of dollars worth of value, it doesn't necessarily get all that much funding from entities that should be interested in doing that work. So I don't know if I answered your question.
Yeah, it sounds like it's not happening anytime soon. Yeah. So
Yeah. But we certainly can make steps towards that. Like just like doing libsecp is something that would be feasible, and that would be certainly a great start. Fabian has a question.
It's not the direction, my question. So what is your opinion about putting formally verifiable code as part of BIPs? And then in particular, are you familiar, and what's your opinion on HackSpec and Hacks? The background being that Jonas and Tim have put some HackSpec code with some BIPs in the past, but then recently they switched back over to Python and done this SecP lab library. Yeah, I would be interested in your opinion in particular, because I'm looking into finalizing the half-egg BIP, and I'm thinking about this.
Yeah. So I'm aware of HackSpec, but I wouldn't say that I'm familiar with it. My guess is that it's probably something that's best decided on a bit-by-bit basis of whether it's worth that effort. And I would probably actually engage with Jonas and Tim, who probably have more, who are familiar with, of course, HackSpec, and probably have significant opinions on whether it's worthwhile or not.
Okay, thanks.
Just a couple minutes left. Anybody else with a question for Russell?
Michael?
I was wondering, do you know or are aware of any work that's gone into formal verification for alternative Bitcoin clients? I know there's a Haskell client. Have you seen any work there, poked around there at all?
No, I'm not aware. This is the only Bitcoin-related formal, other than the HackSpecs. This is the only Bitcoin-related formal work that I'm aware of. This doesn't mean there isn't anything out there, but yeah, nothing that I know of. I will just part by one thing, is that writing these formal specifications has actually been very helpful for me. It influences the way I comment my functions, right? So I sort of give a much lighter version in human syntax for like this notion of separable conjunctions, but the preconditions of the heap and stuff like that, and listing out sort of the propositional preconditions they have. Not necessarily suitable for all routines, right? But it's definitely influenced the way that I comment my C code nowadays.